Now we will talk on PyTorch. We will study PyTorch, which is used for the practical work of homework 4 and possibly projects on deep learning. So basically some basics on PyTorch. PyTorch, it's a library that allows doing deep learning where we have automatic differentiation implemented. This is not the only library doing this but this is one of the widely used, widely known library that is achieving that. That means that all the question of computing the gradient, the derivative of the models is done automatically built in the library. So no need to define that. And the really great thing about this is that it can allow to define custom models where backprop will be applied directly through automatic differentiation. And these automatic differentiation models are easily compiled for running on GPUs, for example. So it has been released early October 2016 by a Facebook team. It is built over the Torch C engine. So it is Torch, which is a relatively old framework, but so they use that framework to define PyTorch. The way it is implemented, it is more what we call Pythonic. It is more in line with the guidance on how to develop to do Python than with TensorFlow, because TensorFlow is based more on manipulation of the graphs directly, some complex graph where there is tensor flowing around the different edges of the graph. PyTorch is more built on doing things in terms of programming the way we should do things in Python. So the syntax is quite close to the NumPy syntax in terms of managing the tensors directly. So the nice thing over the automatic differentiation, like I said, is the fact that we can get the models to be run on GPU very efficiently. So it is extremely fast. We can get a factor of 10 easily, even close to 100 factor in terms of acceleration, depending on the GPU, depending on the type of processing we are doing. So that's really neat. That really allows us to exploit GPU seamlessly without having to program them explicitly. And another thing compared to TensorFlow is the fact that the graphs, which describe the processing done within the networks, the neural networks, it can be done dynamically. So there can be choices, way to process that can be changed at runtime. It's not something that we are compiling when launching the execution and sticking to the static representation of the graph. And as such, it is stable and usable for large-scale development, deployment. Facebook has developed layers of that and other teams to allow using models built with PyTorch in production. So the PyTorch, like most of such libraries, organized around the notion of manipulating tensors, including automatic derivation. So we are creating tensors of different type. So we can call the function torch the type we are looking for tensor. So it will build a tensor of these values. For example, if we are building a tensor of floats, the statement here will allow us to build such tensor. We can create a random tensor with random values, say normal distributed values. For example, I guess it is what we got with an n, or maybe using other distribution. So we just need to provide it the shape of our tensor, and it will create a random tensor with the values we are looking for. We can also create a tensor from NumPy array. So if possibly we have read or we are manipulating data which are in NumPy array, we can import them, convert them into TensorFlow using the from NumPy function directly. And the point is that we can perform all kinds of operations on the tensors. Remember, tensors are pretty much the generalization of matrices. So it's basically multidimensional arrays of values. And as such, we can do, for example, if we have two tensors of the same shape, we can add them directly value-wise. So we get all these values added together. So the plus operator here is defined. So we have a plus b equal to c, and we see that the value is c corresponding to at each position in the tensors a and b. We take the value at that position and we add it to get our result here. Also, there is a full list. So we have the full list of operations that can be done at that link. So during the application of the operations, PyTorch builds a graph of calculation. So this graph is somehow recording all the operations that we are doing on some of the structures, data structures of PyTorch. So we are building up a graph with these operations, and from that graph we can implement automatic calculation of the derivatives at each step. So the point is to get for each operation the function that allow to get the derivative, but if it is when it is done for that operation that is applicable, the code is applicable in relation with the other operations. So and all this is managed quite automatically, quite well within PyTorch. So we only need to indicate then when we are building up the tensors, we are indicating whether or not the calculation of the derivative with certain tensor is required. So we can then also set that once a tensor is in place, we can set it as a tensor where we want to get the derivative, compute the gradients. So for example, if we are doing a linear regression test, we want to create this. So we can declare weights, vectors, and random biases. So we just set, for example, in 10 dimensions, the tensor W, which is and the bias B. So we are building them with 10 by 1 for W and 1 by 1 for B. And then we can execute the classification according to a linear regression model. So it's basically linear regression. We have a X. We want to evaluate the Y at value. So simply take W dot X plus B, which correspond to our basic linear model. We are able to obtain W at here. And we can then compute the quadratic error from that. So the quadratic error is the Y at minus the target Y power of 2, so 2 stars, all this multiplied by 0.5, 1 over 2. And this is it. So this is the way to compute the prediction, compute the error on that prediction. And from that, we can derive the equations using the method backward to make some adjustment to the W and B. So we can recover the gradients here by getting, say, W dot grad for the gradient over W, B dot grad for the gradient over B. And then we can take a step by gradient descent in the right direction. We could just only state that W is equal the previous W minus eta learning rate times gradient over W, and likewise for B, for updating the bias. So with all this, we are able to implement linear regression with TensorFlow, with PyTorch, that can run on GPUs. It's overkill here because the task is very simple, but basically we can get this all directly like that without having explicitly to state to implement the gradients. So all tensor operations can be easily performed on a GPU. So we can have then the version of the tensors that are CUDA friendly or running on NVIDIA hardware. So torch.cuda.type sensor is similar to what we see before, but is made to be executable on GPU. And then we can translate tensors from a non-GPU type, non-CUDA, to a GPU type CUDA, simply with this method. We just have to say we convert A to B on the GPU. So we say to CUDA. So it allows us to convert A to a tensor for the GPU. And if we want to do the other way around, we want to take a tensor on the GPU to move it on the CPU. It's again a 2, but CPU there.